Does anybody have any questions about anything before we start?
There was one problem on the chapter 1 homework. It was like confusing. It was the solution one is set a minute.
Yeah, I can do that after class.
Okay.
I don't want to.
Yeah.
Okay, so we started off talking about types of different bonding, and ionic is opposite charges attract, like charges repel, and covalent is sharing electrons. A metallic bond is like a sea of electrons. And now we're going to move on and talk more about some of the different things with chemical formulas. All right, thank you. And it's hard to see this. So we're going to learn about names soon, but some molecules we give special names. So of course, you know, at the beginning of class, I mentioned water, dihydrogen monoxide, H2O. But here's a common one down here, ammonia, NH3. We don't call it nitrogen trihydride, for instance. But here's some other ones. Benzene, we don't see this too much these days. I think I told you that chemistry was more or less taught the same way since 1960. And benzene was a little more commonly used back then. We don't use it as much right now. And acetylene, we use acetylene quite a bit. They use it in welding torches. But notice something, so benzene is C6H6 and acetylene is C2H2, but has a 1-to-1 carbon hydrogen elemental ratio. That the simplest ratio is called the empirical formula, and we'll talk about that a little bit more later. Structural formula, we haven't really got here yet. We're going to do this mostly near the end of the semester. And these are just different types of models. This is also known as a Lewis structure here. And here are different models. Here's a ball and stick model and a space filling model. So oftentimes you see models, think of like a model of the space shuttle. It's smaller. So, but in case of molecules, the models are bigger than the actual molecule. So that's probably a little statement of the obvious, but and more classification. I mentioned this before about pure substances. Pure substances are either elements and compounds. And elements can either be atomic or molecular. So although metals are also considered to be atomic, so atomic solids. So molecular, so like diatomic oxygen, the oxygen that we breathe is, so I even said diatomic, 2 atoms here. And then compounds can either be molecular, just like molecular elements. They can be molecular or they can be ionic. And what's the difference? Well, the bonding. So covalent compounds, molecules, they share electrons. And ionic compounds, there's a transfer of electrons. And you'll notice as I go through the semester, I say things over and over again, just more detail later. So let's classify these things. And so first one here, xenon. Xenon is an element. And actually I have a periodic table shirt right now. So xenon is here on the far left. So it's a noble gas. And noble gases tend to be just, they don't bond. They're atomic solids. Now you have nickel chloride. Nickel is right here, here. And this is a metal. These are the metals here. And chloride's over here. So it's a halogen, it's a nonmetal. So you have a metal and a nonmetal. And metal and nonmetal, then that means ionic compound. So this is an ionic compound. Bromine is a nonmetal. It's also it's a molecular, well, it's not a molecular compound, it's a molecular element. And this is, you don't necessarily have to memorize this right now. I'm not really gonna test you like, well, which one? Xenon is an atomic element and bromine is a molecular element. That's not something I'm really gonna test you on, just so you know. So, but the nonmetals that are not noble gases, they tend to form molecular elements. Nitrogen dioxide, these are 2 nonmetals. So nonmetals tend to covalently bond. So this is a covalent bond. And then we have sodium and NO3. We'll learn later, this is a polyatomic ion. Nitrate, so polyatomic. So poly means many. So a monatomic ion, that's mono. If you're a monogamous relationship, you're with one person. If you're a polygamist, you see many people, right? So monatomic ions means one atom. Polyatomic means many atoms. And so nitrogen and 3 oxygens, they come together and they form a -1 charge. That's a polyatomic ion. And sodium here is just a metal, well, metal ion, sodium +1. This is an ionic compound. So, questions so far? Okay. Does anybody like to play Romeo and Juliet? I always think of Juliet, say, what's in a name? Right, would a rose smell as sweet? So we're going to talk about names now. So what is in a name? And we have a formal way of naming things. And if you must know, the Center for Forming Names of Compounds is actually in my old stomping ground, Ohio. It's in Columbus, Ohio, is where they have the international committee that decides the names of things. So if you ever wonder how they decide to name something. So from elements to compounds. So, but this is what we've all agreed on. So we've all agreed to name things this way. And let's start with the easy ones. So binary. So binary means two ionic compounds that contain a metal that has only one type of cation. So remember, cation, positively charged ion. So for instance, so for you say the name of the metal, you just outright say the name of the metal, then the base of the anion, in this case a non-metal, then plus the word the syllable ide, IDE, ide. So for instance, a calcium ion, calcium is an alkaline earth, tends to be +2. Bromine tends to form the -1 ion. So there's 2 bromides, so the 2 -1s to counteract the +2 charge. So calcium and 2 bromines is known as calcium bromide. We don't have to include any other numbers there because calcium will only form +2, bromine will only form -1. Do you have a question or are you just playing? Oh yeah, okay, that's fine. You play the hand. Just before we're talking about how it's hard to read social cues with the masks on. So
back to that one slide. Wait, here it is. Base name.
yeah,
Yeah.
base name.
Uh,
So bromine, so you short it to brome, and so bromine, brome, then ide, bromide. And I know there's not really a convention over like, how do I decide what the base is? So question?
So most gases will have the ide if you're having a compound for all gases.
Yeah, for metals and nonmetals. Okay, and what about things that have more than one ion? So many metals have more than one ion, and how do we distinguish them? So the way you do those is you name, the metal doesn't change its name, at least in the current formal way of saying things. Metal keeps its name, and you either say the charge of the metal, or you write the charge in Roman numerals. And then the same thing with the non-metal, base plus IDE for the non-metal. And Roman numerals, if you wonder how it works, that's how it works. I is 1, V is 5, X is 10, L is 50, C is 100, and M is 1,000. But you probably won't have to go past 6. So that's how you count from 1 to 10 in Roman numerals. And a lot of times you join the lines together. So 1 is I, 2 is II, 3 is 3 I's, 4 is 1 less than 5, IV, 5 is V, 6 is 5 plus 1, so VI, 7 is VII, 8 is 5V plus 3, VIII, 9 is 1 less than 10, IX, and 10 is X. So that's how you do the Roman numerals.
move it to the side, please.
Which side? This one here?
No,
Where
I
do
don't
you?
need ordinals, just this.
Okay. So for instance, you know the notes are online too.
I know, it helps me study this one.
Okay. So lead, for instance, and so just so you guys know, I know like you're like, oh crap, I have to remember all this stuff. remember the tests are open note and open book. So you can just kind of remember where things are. Lead usually can be +2 or +4.
Oh, it is?
Yeah, it can. So lead changes. It can have more than one ion. Common ones are +2 and +4. You can force lead to have other ones. So, but that's less common. So lead. So how about PbCl4? And you can even see that I'm kind of, that's another way of saying that this is not a formal way of saying, we don't say, you're not supposed to say PbCl4, but I'm just said it, right? So you'll hear that commonly, but the proper way of saying this is lead 4 chloride, or writing it out as lead, the metal name, IV or 4, you don't say lead IV, you say 4, and then chloride. So chlorine, chloride. Why is it 4? Because chlorine tends to form -1 ions. So 4 -1 charges here are balanced by a +4 charge here. And I'm just going to mention these quickly. This is not going to be tested on, but you might see this in other places. You can use this old way of saying things. So like iron, for instance, iron +2 is ferrous, and iron +3 is ferric. And here is an old, you guys want to see a chemistry joke? Let's see why chemistry humor is so terrible. Anyone want to guess what I'm drawing?
Ferris wheel.
You got it. There you go. Yes, a Ferris wheel. I'm impressed, Andre. All right. So, but truth be told, I don't even remember that, to be honest with you. I'm a PhD in chemistry. I can't remember that. That's the old way of doing things. So I'd have a beard down to, I'd have like a Gandalf beard or Dumbledore beard if I would use that convention. So, all right. So I mentioned polyatomic ions. I remember open note, open book. Although I say that, but one of the cautions with that is, if you guys are going to go and take something like the MCATs or the GRE in chemistry, you're gonna have to remember these things. They're not gonna provide them for you. But I want you guys to focus on learning, because I mean, chemistry is like, a lot of people see freshman chemistry like a freight train coming at them, because there's just so much stuff and we change topics so much. And then you learn the exceptions to rules, you learn the exceptions to the rules, that kind of stuff. So I'd rather just have you guys trying to focus on the learning and the logic than that question.
You said this is for the PhD in chemistry, right? The test?
For the the graduate record exam, that is, I mean, if you don't know common polyatomic ions, you're not going to get a PhD. But I mean,
This is used in the MCAT for like when you go to medical school.
yeah, you will have to remember this if you take the MCAT, or if you take these standardized tests like the graduate record exam subject for chemistry, or the MCAT exam. So for pre-medicine, right? So you will have to remember that, but like chemistry is a big part of that, or a moderate part of that. But I'd rather this class you focus on learning than have to worry about some little memorizations here and there. You'll probably remember it as it goes along. Yeah.
Will it help?
I don't know, to be honest with you. I guess in a way I can't empathize, because I was born and bred to be a chemist. So I'm like, of course it's cyanide. Why wouldn't it be cyanide? Cyanobacteria, right? It makes all sense. Everything's connected. So, but I mean, that's how I remember things actually. When I said cyanide, I remember cyanobacteria, blue-green algae, fixates nitrogen, carbon, base light forms, cyanide, CN. It's just big loop in my mind. Right.
Language.
Yeah. Yeah. There's actually chemistry is second language. There's a book about that. But anyway, that's how my brain works. So however your brain works, I'd rather not have you like, oh crap, I gotta get a flashcard. Remember perchlorate is ClO4. I'm not going for that. So I said briefly mention and we're having a conversation. All right. All right, so ionic compounds, let's talk about molecular compounds. The way that you talk about molecular compounds and name them, you have a prefix, and this is for nonmetals. Prefix, the name of the first element, prefix, the name of the second element, plus IDE. So I know next question is what order do I put the elements in? So at this point in time, try not to worry about that too much. The answer to that question is you tend to put the bigger and or the least electronegative element first. You'll learn about element size and electronegativity later, but there is a convention for that too. But so prefix, and the prefixes are mono is 1, di is 2, tri is 3, tetra 4, penta 5. And it goes, does it have more in there? Okay, there we go. Hexa 6, hepta 7, octa 8, nona 9, deca 10. So, and there is an exception to that though. If the first element is only 1, you tend to drop the mono. So for instance, if you say something like CO, carbon and oxygen, it's carbon monoxide, mono 1 oxide. You don't say monocarbon monoxide. You drop the mono for the first element, if it's 1. If it's, well, an example, this one here, I guess I'll jump ahead. This is going to be, so tetra. Oh, you don't need to spell the P. Okay, I'm just tetra phosphorus deca sulfide. That's a U. And if you notice, tetra deca, right? It's not 1, so I have to use the prefix tetra for 4. The name of the element, phosphorus. There's 10 deca sulfide, so sulfide. So you name this one tetraphosphorus decasulfide. I know I'm kind of going backwards, but I was using CO as the example. Okay, and then the other ones here. So how would you name this one? Ni3. So nitrogen and iodine. So you would name you drop the mono because you don't, it's 1, you don't need the mono. So then you just write out nitrogen triiodide. And I tell you, if you have a spell checker for a word processor, they hate it when you name compounds. So you're going to see lots of red squiggly lines. Yeah.
Because it wants you to put like a abbreviation or a dash between 2 eyes.
They just don't keep them in the dictionary.
Okay. Yeah.
I mean, how often does nitrogen triiodide come into? I mean, not the majority of the world are not chemists. Some of that horrifies me, I realize, but majority of the world does not, write out nitrogen triiodide. Whereas the word, did I spell the word phosphorus right? I usually spell that one wrong. Phosphorus and fluoride, I always seem to spell wrong.
Right.
So, and then B, so PCl5. So P is phosphorus, you drop the mono, so you just write out phosphorus. And then 5 is penta, and then chloride. So, and notice that I'm just highlighting because you can see. So you drop the mono, just phosphorus, and then 5 chlorines, pentachloride, phosphorus pentachloride. Question, yeah?
Do they always call it water if it's H2O? Or do they say it's dihydrogen monoxide?
No one calls it dihydrogen monoxide. Yeah, I mean, that would be the proper name. But I mean, ammonia is also not nitrogen trihydride either.
Okay.
Right, so, and I mean, to answer your question, no, some Spanish calls it agua, for instance. I mean, right, it's not always water, it's different languages, but it's such a common molecule that we don't change the name. Okay, and so we're still on naming and acids. So binary acids, so binary, 2 atoms. And so we haven't learned this yet, but acids, they add hydrogen. So we'll talk about this much more in depth. We'll talk about a little bit in chapter 5, a lot more in 162 if you stay with the University of Hawaii sequence. So, but acids work, they add hydrogen, they add positive charge specifically, and acids taste sour, which says bases taste bitter, right? So, but acids, and binary acids are the ones that have 2 atoms to them. So hydrogen and chlorine form an acid, also known as hydrochloric acid. It has a common name called muriatic acid. So a lot of times you'll have even more like common names besides just the scientific name. So, but HCl, this is known as so chlorine chloric acid, hydrochloric acid. I said before, like it has some common names. So muriatic acid is the common name for that. Not many people call it muriatic acid, at least not anymore. Maybe like Sherlock Holmes would. Okay, so, and to complicate things even more, we have oxyacids. So what are oxyacids? Those are acids that have oxygen in them. So that's one thing about science. The nice thing is a lot of times the names tell you quite a bit. So like the word chlorofluorocarbon. So like celebrity Jeopardy question, right? What elements are in chlorofluorocarbons, right? Chlorine, fluorine, carbon, right? So the name has that. So oxyacids are acids that have oxygen in them. So names tell us quite a bit in science. Oh, I need to charge my Apple Pencil apparently. And okay, so and if you have an oxyanion that ends with ate, you say it's ic acid, and if it's ite, you use us acid at the end. So how do you remember the names? And there isn't really a good convention for how you name things. And the answer is up here, you have these polyatomic ions. You can see like chromate, dichromate, and things like that. So that's how you name, you name them that way. And so, for instance, SO4 minus 2, that's the sulfate ion. So H2SO4, that's sulfuric acid. And SO3 minus 2, that's sulfite. And so then H2SO3, this is sulfurous acid. And a little bit even further. So what do you do if you have an extra oxygen? So here is chlorate, so that's chloric. And this is chlorite, so that's chlorous. If you have one less oxygen than the ite, it becomes hypoite. And so this ClO is hypochlorite. And if you add a hydrogen to it, it's hypochlorous acid. So bleach is NaClO, that's sodium hypochlorite. And then you can go one up from the 8. And so the ClO4 minus, that's the perchlorate ion. So that's 1 plus oxygen. And if you add up a hydrogen, then it's perchloric acid. So that's the naming convention. And I'm going a little bit further than the book has. But but you might see some things, perchlorates, they're used in cheap fireworks. They're explosive. So, and I already mentioned bleach is sodium hypochlorite. So I use bleach all the time. So, okay, here is a flow chart. If you like flow charts. So this is just what I covered so far in the past 25 minutes. Ionic metal, nonmetal. If there's only one ion, you name the cation, the base of the ion plus IDE. If there's more than one for the cation metal, you include the charge, you say the number, you write the Roman numerals. For molecules, prefix, name the first element, prefix, name the second element, the base name the second element plus IDE. You drop the mono if it's 1 for the first one. You do not drop the mono for the second. Then acids, Binary acids, so just two hydrogen and other elements. It's hydro, base name of the nonmetal, plus ic acid, so hydrochloric acid, hydrobromic, hydrofluoric, hydroadic, that kind of thing. So they're oxyacids that are polyatomic ions that contain oxygen. If it's 8, you put the ic in front of it, or you drop the 8, put the ic. So phosphate is PO4 minus, H3PO4 is phosphoric acid. And then if your oxyion is an ite at the end, you change the ite to the us and you write the word acid. So sulfite becomes sulfurous acid. So questions so far? All right. Naming command. How about Zoom land? You guys doing all right?
Yeah.
You would never know that we have 8 other people in the classroom coming to you live from their couches. Okay. So moving on, I already mentioned a bit about the mole, and but I know I'm going to expand upon it. It's interesting teaching this class versus teaching like a really like a non-majors or a developmental sort of class, because we would spend a lot of time talking about moles. But it's just moles is one of many concepts. We draw pictures of things and dozens and say this is just like a mole, but we really just jump right into it. And I was just thinking about it on the drive over here. It's kind of a cool lab. I was thinking about that when we were doing the atomic mass. There's at least St. Anthony's, St. Anthony's in Maui, they have a lab where they take different types of candy and then they weigh them together and they get an average of the weight. And then they say, oh, this is kind of like the way different isotopes are and the atomic ratios. And this is why you have an overall average. And then the kids get to eat the candy and they love it. So we're not going to do that in this class, unfortunately. Also, certainly not with COVID restrictions. I can't even get within, I'm allowed to be within 3 feet of you. That's about as good as we can get right now. And you can be within 3 feet of each other. All right, well, going back to mass and moles. So we learned before about how we figure out the number of moles of elements. So 12.01 grams of carbon is a mole of carbon, which means you have 6.02 times 10 to the 23rd, because the bottom number on the periodic table is 12.01. And that is the weighted terrestrial average of the different isotopes of carbon. So weighted because it's an average range here, terrestrial here on Earth, and we get about the same amount of average, and then we have that number on the bottom of the periodic table. So, and then we do that for elements, but what about compounds? So compounds, the way that you figure that out for compounds is just like the elements in the periodic table. You just take the number of each type of element, you multiply it by its coefficient, you sum them up, you add them together. So and we call that the formula mass. So when you have something joined together, it becomes something new. It has different chemical properties. So, okay, let me show you an example. So 6 carbons, 12 hydrogens, and 6 oxygens. This is also known as the molecule for glucose. There are different isomers. So isomer means same number of atoms, but different connectivity. This is the same structure. This is the same ratio of atoms for fructose as well. Same for other ones, the mannose. It's what's found in cranberries. So these are different sugars. They're isomers. So fructose and glucose are 2 different molecules. They're connected differently. We'll learn about that later. You saying something?
I say glucose. So
yeah. Yeah. So this is also known as hexoses, or 6 carbon sugars. So what is the formula mass for glucose? And so you look at this formula for glucose, C6H12O6. This formula, subscripts tell you that there are 6 carbons. So the way that you figure out the moles of this, you start off with 6 carbons, and carbon is 12.01 grams per mole. And you get that from the periodic table. So here is a picture of the periodic table. And notice carbon here in the bottom, 6 protons, 12.01. And then you sum up then 12 hydrogens, 1.008. And then 6 oxygens, 6 times 16. And the sig figs on this, I guess I'll go ahead and list the sig figs. I'll give everything 4 sig figs, so I'll be proper. I know it's 180 because I have it memorized. So this answer here is going to be 180.16, I guess for sig figs, it would be 180.2. And the units here are grams per mole, which means that you need 180 grams of glucose. If you have 180 grams of glucose, you have a mole of glucose, means you have 6.02 times 10 to the 23rd glucose molecules. That's a lot of glucose. That's about a half a pound. So not quite a half a pound. That's a lot. So, all right, recap. How do you do this? How do you figure out the formula mass of glucose or anything else? You sum up the number of each element and then the atomic mass of each of those element, and you take that formula, sum it together. So there's 6 carbons. Carbons got 12.01 grams per mole. I guess I should show this room inside the room some love. You guys over there, you see all my gestures. Oxygen here, you can't see that's 16. I'm sorry, hydrogen. Hydrogen on top. So 12 hydrogens. Hydrogen is 1.008. Oxygen 16. So 6 times 16. You sum it up, you get 180. So, questions so far?
Yeah. So glucose and fructose weigh the same.
Yeah, they do. But they're very different. They taste different. Fructose is sweeter to us humans. Okay, so now the dimensional analysis. So I mentioned you'll see lots and lots of dimensional analysis. An aspirin tablet contains 325 milligrams of acetylsalicylic acid. How many acetylsalicylic acid molecules is contained? By a stroke of luck, actually, aspirin is 180 grams per mole. That's not a very common number, though. So for sugars, it's common. But acetylsalicylic acid, what is it exactly? It's 180.15. So this, we've already learned how to do this. So this is 180.15 grams per mole. So how do you solve this problem? And the way we're going to do this is dimensional analysis. So you can skip steps. My teachers used to yell at me all the time about skipping steps, but I love skipping steps. There's 2 ways to do this, and you can skip steps if you want. You can include all the steps, however you like. I would normally just write 0.325 grams, but you can do it this. I'll do it properly. What the heck? 325 milligrams. I'll just put A for aspirin acetylsalicylic acid times, so gram, 1,000 milligrams. And then, okay, so I remember we're trying to convert, so we're going to figure out the number of molecules. So we have mass, and one of the automatic things I should try to have you in your head convert mass to moles. So I should say grams aspirin, milligrams aspirin. Then so that means you have a mole of aspirin to 180.15 grams of aspirin. And then we're going to have moles of aspirin. So you have 6.02 times 10 to the 23rd aspirin molecules per mole of aspirin. I just didn't really want to write acetylsalicylic acid many times. I just wrote capital A instead. Because I'm lazy, and laziness can be a virtue. So, and I mentioned before, one of the things that I would do, I would probably just combine these steps together and just write 0.0325 grams. So that is a totally valid way of doing things. But you guys are learning, you can deal with my skipping steps later, I guess. So of course, the check with this, milligrams cancel, grams aspirin cancel, moles aspirin cancel, and you get aspirin molecules. And the nice thing about dimensional analysis is if your units work out, you're probably right. So, and then doing this, you get 1.09 times 10 to the 21 aspirin molecules. So that means when you take a tablet of aspirin, that's what you're going to get when you take that. Okay, so recap for this one. And if you wonder why I do recaps, I guess I always talk about why I'm doing my method to my madness. If you study teaching theory, my role is, and there's a couple of different theories. My role, the instructor, among other things, is best described as I need to communicate clearly. And also my role as instructor, I need to communicate clearly and I can teach specific concepts. And then the idea is, what's your role as a student? Well, the role of the student is to learn. Also, the role of the student is to combine the subjects together. I think my way of doing these recaps, if you want to do recaps, I'm trying to help you connect the things together. So seeing the forest from the trees is oftentimes the analogy. Because we're combining different things. We've learned about molecular weights, and now we're going into combining it with dimensional analysis, right? So we're taking two different concepts and bringing them together. So that's the recap. I'm saying, okay, let's look at this. Now that you've seen each of the step, let's combine it back together so you can kind of cross the wires in your brain. That's how humans learn. So dimensional analysis. So we have 325 milligrams acetylsalicylic acid. How many aspirin molecules is that? So we start off with mass of aspirin and then divide by the molecular weight of aspirin, acetylsalicylic acid. And then now we have moles, and the moles, when you multiply by Avogadro's number, you get the number of molecules. And then you can see the units all cancel out, and we're left with 1 times 10 to the 21 aspirin molecules. Question?
And that number is how many molecules are in 325 milligrams?
Yes. Yes. 2, 3 sig figs. Yes. Other questions? Shoot. So I don't use aspirin very often. And this is the first time you're seeing this. I usually do this. So when you study evaluation, there's 2 ways to do evaluation. It's formative and summative. Formative is on the fly, and summative is after the fact. Tests are summative. So formative, it's kind of like if you're a coach and someone's playing basketball, the formative is like, take the shot, dribble, run over there. That's formative. That's formative coaching. Summative coaching is, okay, we lost the game and you just need to work on your free throws a little bit better. You need to run towards the ball. That's summative. That's after the fact. So this is my formative assessment. I want to see how well you understand something. And if you get it, I move on. If you don't get it, I try to figure out what's wrong. And then I do what I can to correct that. So this is your turn. We've just learned how to do molecular weights. So how many ibuprofen molecules are there in a 200 milligram tablet of ibuprofen? And I'll go ahead and give you some numbers. Carbon is 12.01, hydrogen is 1.008, oxygen is 16. If you want, you can abbreviate it to 12, 1, and 16. Normally I go around the classroom, but this is going to be interesting. Like I said, COVID versus. So who here is deer in the headlights? You have no idea what type to do. Anyone feeling that way? Okay. see the top there with the aspirin, you have the 325 milligrams of aspirin.
Yeah.
So it's going to be the same setup. Right. But instead of 325 from 200. And instead of 180.15, I don't know what it's right. Calculate that up. Okay. So there's 13 carbons, 18 hydrogens, and 2 oxygens. So it's 13 times 12 plus 18 times 1. Plus. You see where I'm in the 13? Is it bottom?
Yeah.
18 times 1 for hydrogen. And 2 times 16. You sum that together. That number's going to be different. It's a 6.02 times 1. That's all. Multiply the top numbers, multiply the bottom numbers, divide, and you just go across. I don't know if you were listening. So the way it's the same setup as the problem above, but instead of 325 milligrams, it's 200. And instead of aspirin, it's ibuprofen. So does anybody have that number? What's the molecular weight of ibuprofen?
Ibuprofen is 206.3 grams per mole.
206 grams per mole. So it's going to be 0.02 grams times mole over 206.
So the 206 would be where the 180 is?
Yeah. Guess I should have warned you guys. Bring your calculators or your cell phones to class, and your cell phone should have a calculator, or does it?
It does, but it's better in my head.
Okay. Videos are also online. You can even jump ahead and look at the answers.
So from that, 0.2 grams times mole over 206, I understand you substituted the 80.15 grams of aspirin over the 206,
Yes,
and that represents the total
that's a molecular mass.
molecular mass.
Yeah. So how are we doing? How many people think A? How many people think B? How many think C? D? Okay, so we got about a third of the class. The answer is B. Answer is B. So let's apply some logic. So we have A. Actually, if you take this, you should right away know that's going to be A or B, because molecules are tiny and it's going to be a huge number. So 5.8 or 5.8 times 10 to the 23rd to 20th. That's a big number. 206 in terms of molecules, 206 is nothing. We're talking like nanograms here. So 206 is too small. And D is a fraction. You can't have less than a molecule. So when you deal with chemistry, a lot of times you deal with a type of mathematics called discrete mathematics. So meaning you can't have less than wholes. So meaning like, I remember doing some industrial engineering once as an intern, and I calculated I need 2.3 people on one stage of a line, and which means I need 2 people, right? I can't have a third of a person. You can only deal with whole people. Same thing with atoms and molecules. You can't have half molecules, you can't have half atoms, you have to have whole numbers of things. So this one's wrong by the nature of discrete mathematics. This is too small. It's A or B. So when you get multiple choice tests, logic your way through it. So it's got to be A or B. And probably even looking at this, I would have guessed B anyways, because the whole mole, I would know like it's going to be, this would be around 200-ish grams. So, right, because you have a molecule that's big. So aspirin's 180. So you're going to get 200-ish grams of something for, and this is about a mole. That's going to be about 200. This is also what's known as a order of magnitude calculation that I'm doing right now. So does this make sense? This one doesn't make sense. This is the only one that makes sense. But then if you do the math and you calculate it out, you do get this one, in fact. So questions with this one?
I have a question.
Please.
It says the 10 and the 20 for the second one.
Yes, 10 to 20.
Yeah. How did that change? That one. Yeah. So there was 23. Right?
Yeah.
So where did that change?
Thing is, I used to have a crappy old calculator that showed all the steps.
It was the best.
And now the batteries are dead. Okay.
Want to use mine?
Oh, okay, I got it. I got it.
All right.
I missed that part, yeah.
What was it?
Huh?
It's just,
What was it?
The significant figure?
Okay.
oh, okay.
Wait, I have a question about
Question.
rounding.
Yeah, I only listed
You
it. It's not, I didn't, it should be 3, but I put as 2.
Okay, so like for the actual weight, like I see that 12 doesn't have 12.01.
Yeah.
So why does that happen? Or what what's the logic behind that?
Where the 0.01 comes from?
Or no, why do you take it out?
Because I'm just trying to do it quickly.
Oh, okay.
Yeah. I'm accepting the error. I'm being a bad scientist in that regards. So it just depends on your application. I mean, where I've worked on, whenever you do stuff with baby formulations, you got to have a trillion freaking digits. That people tend to be really concerned about baby food and baby medicines, for instance. And so I remember doing calculations where there's tons and tons of digits, extra tests that had to go on for baby products. But then you have something like soap, you're like, meh, bucket of this, bucket of that, stir it together, good enough. Check the pH at the end. All right, next, kind of thing. So it just depends on your application. I know I'm like I said, I'm kind of a practical chemist. So, all right, other questions? All right, so how many atoms? How many atoms are in the ibuprofen tablet? Not, I mean, I know there's starch and binder and that kind of stuff. But how many atoms do we have in this 200 milligram ibuprofen tablet? How many atoms do you have in these 200 milligrams of ibuprofen? So let's logic our way through this. So 13 plus 18 plus 2. So there's 13 carbon, 18 hydrogen, 2 oxygen. So 2 plus 18 is 20 plus 13, that's 33. So a lot of people pick 33, but that's for one molecule. We have 5.8 times 10 to the 20 molecules. So we already know right away that A is wrong. So it's going to be 5.8 times 33. So 6 times 30 is, it's going to be it's going to be 180. So 180 times, I'm going to see I'm estimating 5.8 by 6 and 33 by 30. 6 times 10 to the 20 times 30 is going to be 180 times 10 to the 20. I mean, 1.8 times 10 to the 22. So the answer is C. Okay, you can do this. You can do this the long way. So it's going to be C13H18O2. So the number of atoms, you have 13 carbon atoms plus 18 hydrogen atoms plus 2 oxygen atoms, means you have 33 atoms. Okay? And so you have 5.8 times 10 to the 20 moles. And then you have 33 atoms, atoms per mole. And this is just for this specific instance though, right? So it's moles, ibuprofen, 33 atoms per mole of ibuprofen. And if you multiply this out, you're going to get 1.9 times 10 to the 22nd. But I'm also trying to illustrate, you don't need a calculator for this problem because you already know the number of molecules, which is 5.8 times 10 to the 20. And you can estimate this in your head as 6 times 10 to the 20, and 33, you can estimate the 30. So 6 times 30 is 180. So 180 times 10 to the 20th is 1.8 times 10 to the 22nd. And that's close to C. So that's another that I'm trying to teach you also. There's ways to attack problems. There's ways to logic your way around things. So I'm trying to teach you test taking skills as well. And for me, I've always like, I basically don't time your tests. I give you so much time. You can take as long as you want, kind of thing. But if you need more time, let me know. No one ever really needs more time.
Do you take any tests in class?
No, that's all online.
Gotcha.
So unless you want to bring a computer, I can stare at you while you take the test.
No, it's okay.
I gave you a picture of myself. You can put it in your, in your room.
Probably put it in my car
In the back.
with a mirror, so I check my makeup.
You check your makeup. All right. Well, I haven't heard that. Anyways, how would you sort questions with this one?
Just let me take a picture.
Okay.
No, that is-
I'd smile, but
No, no need.
we wouldn't. Never mind. We're in the mask. How you guys doing, Zoom? Zoomers?
We're still checking.
Wait a minute, wait. Brother, you really go fast.
And as I said before, it is on La Lima.
Sorry.
But I will.
Yeah.
Okay. So if you, last class, I believe, we had a lovely conversation about artificial intelligence and chemistry. And it turns out that right now, chemistry is only a human thing. That computers can't figure out how to do your homework for you. Because humans right now are the only ones that can take these problems, determine what information is pertinent, what information is not, and then attack the problem, solve it. So there are some things that only humans can do right now. So if you're wondering, the CAPTCHA, that stands for something that's like, I know it's a Turing test. So for instance, computers are not very good at recognizing objects and faces. So if you ever do those things like pick all the bicycles, computers have a really hard time doing that. And AI, if you change it, like if you could probably program an AI to recognize bicycles, but if you change bicycles to Christmas trees, computer couldn't do that. You couldn't get an AI that could do both. That could be like, all right, bicycle, car, Christmas tree from a series of pictures. So you could get an AI to figure out how to do every type of mass percent composition problem. You would not be able to have an AI that could do mass percent composition combined with figuring out the number of molecules in an aspirin tablet. So that is beyond our computer capability right now. So this is only a human thing. And we go through these different types of problems. because humans right now, their intellect, we're the ones that can look at these different types of problems and also then figure out how to solve them. So a lot of these like, oh, we have this type of problem. Oh, we have a new type of problem. And this is your training. This is your thinking training as humans. So who knows, maybe when computers get better at recognizing things, we might have to do chemistry problems to get into websites. I would love that day. Everyone else will probably hate it, but that would be a great day for chemistry instructors. So, but calculate so this problem here, calculate the mass percent of chlorine in Freon 112. And Freon 112 is 2 carbons, 4 chlorines, and 2 fluorines. So this is a CFC, also known as a chlorofluorocarbon. Aforementioned, it contains chlorine, fluorine, and carbon only. So mass percent of chlorine. So I remember, maybe you've heard of body fat percentage. So like body fat percentage. So if you have like, this would be a big person. If you have 30 kilograms of fat over 100 kilograms of human, this is going to be 30% fat, right? So if you are a 100 kilogram person and in your 100 kilograms of person, you have 30 kilograms of fat, that means you are 30% body fat. So the way we're going to figure this out is we're going to have the mass of chlorine over the total mass, and this will give us the percent chlorine. And this is going to be percent by mass. So how do we do this? The mass of chlorine. So for every 1 unit of this molecule, we're going to have 4 Cls, and it's going to be over the total mass, 2 carbons plus 4 Cls plus 2 fluorines. And it's looking for chlorine, right? Okay, so 4, and this is 35.45 for chlorine, divided by 2 times 12.01 for carbon, plus 4 times 35.45 for chlorine, plus 2 times 19 for fluorine. So where am I getting these numbers from? I am getting them from the periodic table. Oh, and it disappeared. I am getting this from the periodic table. So carbon here is 12.01, chlorine here is 35.45, and fluorine is approximately 19. I usually just write, I didn't know it was that different. When you look at the textbook says 19. This is my, that's my free app that I downloaded from the App Store. So that's where I get those numbers. And so you sum those up, and I'm going to cheat. Then, so it's going to be 141.8 over 203.8, and it's going to be 69.58%. Okay. And I think, do I have to explain that 69% is 0.69 fraction? I think you probably know that. Okay, so recap for this one. So what's the percent chlorine in this refrigerant? So I'm saying it's akin to like anything. So I'm using the analogy of body fat. What's your body fat percentage? It's the amount of fat you have over your total mass, gives you the percent of fat in your body. Likewise, the percent chlorine is going to be how much chlorine you have over the total mass of the molecule. And the molecule has 4 chlorines. So that's the amount of chlorine, but the molecule also has 2 carbons, 4 chlorines already mentioned, 2 fluorines. And then you put in the molecular weights, or atomic weights, I should say, atomic weights from the periodic table. You don't have to memorize them. And you run the math and you get 0.6958 fraction, or 69.58%. So questions with this one? Yeah.
Is that including 60? 69.58? Or-
Yeah, because fluorine is 19.00.
Okay.
I mean, it doesn't specify how many sig figs. I'll go ahead and. If you really want sig figs, I'll put sig figs. There you go. There we go. Other questions? Yeah.
Seems like you wanted to cover to the end of that many significant figures instead of it just being 19.
It depends on the context. I mean, yeah, I don't like writing. I guess I know I'm being sloppy. Let me show you. I have the. So if you look at the periodic table here in the textbook, see fluorine on number 9. It's 19.00. A lot of times I don't even like write that. Like oxygen, I put 16. I know it's 15.9999998 or something like that, but it actually is 2 sig figs. Oh, that's a. Oop. Who's that guy? Okay. Other questions? Yeah.
Why is it called freon?
That's just, I don't know why they call it freons, to be honest with you. I don't know where that name comes from. Other questions? Maybe I should know. That's something I'd have to ask Google. Okay. So moving on to new type of problem. So hydrogen can be used to replace gasoline as a fuel. Most major automobile companies are developing vehicles that run on hydrogen. These cars are environmentally friendly because their only emission is water vapor. One way to obtain hydrogen for fuel is to use an emission-free energy source such as wind power to form elemental hydrogen from water. What is the mass in grams of hydrogen contained in 1 gallon of water? So, how do we figure this out? We're going to use our favorite thing, which is dimensional analysis. So, meaning we're going to start off with 1.00 gallons of water. I'm going to use W for water instead of H2O. And then we're going to multiply things all the way across. And over here, it wants to do mass. We're going to get over here, we're going to have grams hydrogen. So we're going to go from gallons of water to grams hydrogen. So the way I would do it, I would start off with, actually let's do it my way. We'll see what the textbook does. I would start off by saying 3.78 liters water per gallon of water. Honestly, the reason why I know this is because it's written on milk jugs. So, and then there are 1,000. Oh, well, I need to go from gallons to metric. So obviously I'm going to go from imperial to metric. So I'm going to convert. I'm going to start with liters and then 1,000 milliliters per liter. I guess I should use water. People seem to like to use the proper units. Okay, and now we're going to go density. It's nice that it's 1, but it's going to be 1 gram water per milliliter water. And I know I'm putting the W's here. You can get by without them if you want. It's just I'm trying to emphasize that that's the density of water. Actually, I would do stop there. Yeah, I guess oh no, then we have, so now we had mentioned conversion before. So water, H2O, this is going to be 18.01 grams per mole. And there are 2 grams hydrogen. Why is this going to be 2. Hydrogen is 1.008. It's going to be 2.016 grams hydrogen per 18.01 gram. Okay. So anyways, we have water. We're going to have moles water to 18.01 grams water. And then we have to convert to grams hydrogen. And this is the percent mass that we just learned the concept. They're 2.016 grams hydrogen per. Oh no, I gotta go. What am I doing wrong? Yeah, mole water to mole water. Oh, I was using. There we go. And again, I am multiplying by 1 several times. A gallon is 3.78 liters. 1,000 milliliters is a liter. Density of water is 1 gram per milliliter. I guess it's not necessarily divided by 1, but that's the density. And a mole of water is 18.01 grams. And there are 2.016 grams of hydrogen per mole of water. And I'm getting this number here. And you notice I didn't have to go ahead and figure out the percent mass, that kind of stuff, because if I just know the units and go through. So question.
Would it be easier if you found the percentage of mass and then multiply it by how many grams are in a gallon?
You could do that.
Okay.
That's another way to do it. So there's multiple ways to do it. We can go ahead and do it if you want to do it that way. So the percentage of mass is going to be 2 divided by 8 is about 1/9. Let's see, you're 1/9-ish and 3.78 kilograms. So that's going to be about 400-ish grams. You do it that way, right?
You said 1/9?
Yeah.
How many grams are in a gallon?
Was 3.78 kilograms. So divided by 9, that's so 4 times 9 is 36. So it's going to be a little bit more than 400. I'm doing the Rain Man math.
So 36,000 grams. Right?
Yes.
Yeah. Okay.
Yeah. So it's going to be a little. It should be a little bit above 400.
Yeah. Yeah.
Yeah. How does the book do it? Oh, they did it the way I did it. Okay, good. Oh no, they did. They changed from moles. They added a different step. Okay, I'll do what the. Okay, and I guess it's bad that this is what the book does, and actually you'll see my method is just as fine. 2 moles hydrogen per mole water, and then 1.008 grams hydrogen per mole hydrogen. So, but if you notice, these 2 steps equal that. So, but I guess if you missed the conversation right up here, there's other ways to do it. I know this may frustrate you sometimes as a student that you can do things in different ways, but as long as the units cancel, it's okay. So your valid method, there's many different valid methods to use. So it's not necessarily one valid method works. There's many different ways you could use, and as long as your units work out, and if you notice, I mean, mathematically, I just combined, I know I'm bad at that. I combined these 2 steps together. But anyways, I'll just do what the book does. And again, notice that all the units cancel. So gallons of waters cancel, liters of waters cancel, milliliters cancels, grams cancel, moles cancel, these moles cancel, and we're left with grams hydrogen. And what is going to be? It's going to be more than 400. Is that what? This is going to be 423 grams hydrogen. So that's the way you do that. So, okay. How are we doing so far? Questions? You look a little horrified. Did I horrify you with many different ways? Okay. So I guess the moral of the story is if the units work, it's fine. But there are other ways to solve problems. And so I know you as a student, you're like, okay, what's the proper way? Like, well, there's several proper ways. So, and this, again, this is a reason why computers can't do this yet. So under certain circumstances, you probably would go for the mass percent. So that's another way to solve the problem because we just learned it that way. There are other circumstances where you wouldn't. Sometimes it's easier that way. Like those numbers are handy. If someone said, I have a mass percentage of water, like, okay, I'm gonna go through this long way of doing it. No, you'll probably just use the mass percent. Whereas a computer is a little more inflexible in that. Okay. And do I have time to solve this? I think I do. So we got 4 minutes left, but that's going to be a tough job for you students. Well, I think I'll actually do this. We have 3 minutes left now. I think I'll do this on Monday. Although I know, yeah.
No, I'm asking.
Yes, it does. These lectures are taken directly from the book. So what short week wouldn't be better ended with a song? So here is your song as promised. Oh, is this not showing? Okay. Oh, it's not playing. Oh no, where is? Oh, it's not playing the song. What's wrong with my iPad? Oh, it's. All right. I can't do that. All right. I'm gonna go ahead and disconnect the iPad, and you're just gonna have to listen to it.
There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and golden protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercury, molybdenum, magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
All right, there is your short week. So we'll pick up next time, and you see we're almost back on topic. I know we did a little bit. Oh, I'm gonna send you an email today. I found a really cool article. I'm really excited about it, but you'll see an email.